Everyone. My name is Neerab Kumar. I'm Cloud and GenAI Architect and Microsoft Certified Azure Trainer. I'm very happy and excited to present this video to you. Today we will discuss about the transformer decoder architecture. Although this is quite complex topic, I will try my best to make it as simple or as easy as it is possible. You must have heard about ChatGPT, DeepSeek, Gemini, Grok, and all these are example of large language model. Not exactly like ChatGPT uses one LLM which is called GPT that we will discuss later. Just for understanding and just going ahead, just assume that these are the basically example of large language model. Better if I say these uses large language model. In this session, what we will discuss, what is large language model, what is generative AI models, what is transformer architecture, and we will see how decoder only architecture work. When we discuss decoder only architecture, we will discuss some of the very important concepts of decoder only architecture: embedding, positional encoding, self attention, multi-head attention, and a few more. And I must say, these are not the simple thing to understand. It will require some effort from my side and from your side. And why we are going to try to understand all these things? Because we want to know how does an LLM generate new words, right? What I'm trying to say, if you give input to the LLM, the cat sat on the, then it predict the next word mat. Till now, what I can assume only a human can do this, and that too, trained human. I mean, if someone doesn't know English, he will not be able to predict this next word, or even a child which is not trained, he or she who doesn't know all these things, he will not be able to predict. So basically, only a trained human being can predict this thing till now. And that is what we will try to understand how this machine does it. Large language model. What is large language model is? It is a neural network designed to understand, generate, and respond to human-like text. This neural networks, if you not understand, then you need to go through this to understand. Basically, there are different layers of neurons. There are input layer, output layer, hidden layers. But these are totally separate topics. It required separate videos of this. So basically, an LLM is a neural network designed to understand, generate, and respond to human-like text. Then this LLM only understand or generate text. It does not generate image or your videos. What I'm trying to say, we will see next. And why it is called large language model? Because it has huge number of parameters and it is trained on immense data set. And this large language model utilizes transformer architecture, which is what we are we will try to understand it. So if you see, ChatGPT uses GPT LLM, a large language model. And if you see, there are different version of GPT LLM. Currently, it is 4.5 is going on. We had GPT-4, 3.5, GPT 3.0, GPT-2 previously. And this is very, even if you see GPT-2, which is very small old model that uses 117 million parameters, right? And it was trained on huge data sets. So these are some of the details of this. So that's why it is called large language model. And there is something called generative AI, right? So we had LLM, and now we have generative AI. Generative AI is a type of artificial intelligence that can create a new content like text, image, music, or code by learning pattern from existing data. What I'm trying to say, artificial intelligence system capable of creating new content. It can generate text, image, audio, and other data type. Learn pattern from the existing data to produce the novel output, new outputs, right? And generative AI uses transformer architecture. In fact, generative transformer decoder architecture. You see, I have talked about the large language model and generative AI. Right? In large language model, I told you that it can only generate text or understand text. And generative AI model, what I'm telling, it can generate uh, text also, image also, video also. And most of the people, what they think, large language model and generative AI model, both are same, right? So that means I'm contradicting myself, right? And that is not the case. So you see, if you see the image here, we know this thing most probably. Machine learning is a subset of artificial intelligence. That deep learning is subset of machine learning. I mean, deep learning is also machine learning only. It uses a neural network. But machine learning can use other technology algorithm also. And large language model. So here we come. So GenAI and LLM both are part of deep learning. But you see, all the large language model are not generative AI model. This we need to understand. And all the generative AI models are not the large language. Large language model are those which uses transformer architecture to generate text. But generative AI models, which can generate image and all, it uses some other deep learning technology also, right? So that it can generate images. So this thing we need to understand properly. Many people are not clear about it, right? There are some. We will see some example also coming the coming slide. Here it is detailed. So you see, LLM, which is based on transformer like GPT, it is a large language model, right? But some of the model which can generate image also, right? These are not LLM, like Delhi, Stable Diffusion, Mid Journey. If you see, LLM work with it to describe whatever you write, or it gives it describe the image, right? So this is what it is very important to understand, right? So we see image, audio, video. This uses not only transformer, some other technology also, right? To generate this thing. Transformer is only related to text. Yeah, there are multi-model mm, models are also coming up, which uses text and other media. So, but then internally also it uses other technology. So that include LLM plus other. But like Sora, which uses generate videos, those are not LLM. But LLM help it to do something. What is transformer? Transformer is a deep neural network architecture introduced in the paper Attention is All You Need by Ashish Baswani and his team in 2017. It revolutionized natural language processing and is the basis of model like Word, GPT-5, and many others. So if you see, in fact, the generative AI application and use has become more popular when GPT came into the picture a few years ago. And this all happened because of this one paper or architecture proposed by the Ashish Vaswani team, 2017. It is used to generate, it can be, the architecture can be used to generate new word and process NLP. And this is a paper. And if you search on the Google, you will get it. You can download the paper. This is only 15-page paper, and it describes how this architecture works. If you want to understand how transformer architecture works, you should go through the paper. And if you're able to understand, nothing better than that. Even you don't need to go through this tutorial and waste your time. But the thing is that that's even if you try to go through, unless you're exceptionally good, if you try to go through this paper, it will be difficult to understand the concepts. Why? Because it uses very abstract mathematics like linear algebra, matrix multiplication, softmax functions. It also has some new terminology and concepts like how to generate QKV, multi-head attention, positional encoding as we discussed before. And then there are some layered complexity kind of multiple block, one block does something, other block does something, it communicate with each other, then produce the output. So this becomes difficult to go through the paper and understand, because this paper does not, in not tutorial, it doesn't explain you the concepts. It is propose some technology and how it works in little abstract. Right? So that's why going through the paper is uh, not very good option for the first time at least. So this is what we'll try to do here. Just try to simplify it. So if you anywhere, if you go and read about the transformer, you will see this architecture. And this is also in the paper, from that paper one. Basically has two core component. Left side, what you see, that is encoder. And the right side, what you see, that is decoder. Or in more simplified way, try to represent, depict it. So you see left side is, it is encoder, right side decoder. When you give some input, encoder work on it, um, add some semantic value into it, attention into it, and then pass it to the decoder. Decoder, there are some processing happen, and then it gives to output, and then it is able to generate a new words. Right. One thing, but we need to understand there are two components in transformer architecture. Some model uses encoder only, some model uses decoder only, some model uses both of it, and it does its work as per the requirement. But only those models which uses decoder only part or encoder plus decoder part are generative AI models. There's some model which uses only encoder part, encoder architecture. Those models are not generative AI models, although it is using transformer architecture. This is we need to keep in mind. Here is the detail. The model which is uses decoders architecture, they are generative AI model. They, what it does, it can generate text. Then there are model which is encoder only part. These are not generative AI model. Like what? It is used for classification, prediction, like weather forecasting. Right? So those models are um, using encoder architecture. There's some model which is both like T5 part, encoder and decoder. These can even translate one language to other, like summarize. It can also generate it because it uses this also. So that's why uh, it is generative AI. So now we understand different kinds of LLM and internally what they use. This is also not many people not aware of it. But as per our session and the topic we have selected, we are going to talk about the decoder only model, right? Or this architecture, how this works. This is the architecture we used for generation of the new words. Let me just give some pointer here how it works. You give some input, like we have just seen the cat sat on the, then it can get converted into embedding. Embedding is what converting text into number, kind of. And then positional encoding is added into the embedding. Positional encoding, why? Because input does not go in the sequence, so model doesn't know when which token or which value has come. So just to give the position of the all the words, it positional encoding is added. Then both together, once it is positional encoding added, it is passed to mask multi-head attention. Their attention is added into the in the embedding value of a vector or a word. Then it is passed to feed forward layer again. Then if you see, after mass multi-inheritance and feed forward uh, layer, addition, add and normalization, add and normalization is also happen over there. We add both the output and input of this. It happens in both the layers. Then whatever is output is generated, that is passed into linear layer. There something, some processing happen, and finally get a logits value. What is logits value? We will see. And on the logits value, this softmax function is applied, and then finally we get the probability of the word or token, and the highest probability value is predicted for the next output. Don't worry, I understand whatever I'm saying. Maybe you're not able to understand as of now. So, in the whole session, we will try to understand this thing, what I have told just now. And hope after that it will make sense. So, this is what I was telling. The first, what we do, we give some prompt, like you type something in ChatGPT. Internally, what it happened, each token for timing, or just to make it simple, we say each word is a token, although there are different kinds of token. Just for simplicity, we will take this. Whatever we have entered, the cat sat on the, so every word is a token, which is converted into dense vector using a learn embedding matrix. Dense vector means what? It will convert it into a number, and there's a little bit more that we'll say. So basically, all the words is converted to number. These vectors capture semantic meaning, and that's why I was telling converted into number. But there is a little bit more, because it gets converted a different way, which captures semantic meaning also. Then positional encoding is added into that output. Since the model has no inherent sense of order, positional encoding are added to the embedding. These are fixed or learned vector that encode the position of each token in the sequence. So to give every words which we are taking as a token, to just get the sequence of or position of the each word, we add this positional encoding is added. Then there is a next step, mass multi-head attention. What it does, it allows each token to attend only to previous token, not the future one, ensuring auto-regressive generation. I mean, using this concepts, what model does, it's like when we type the cat, so the cat's how it predicts that, because it find the, it only see the and cat, and then calculate all those probability, and then it is able to predict the set. So during training it doesn't see any future words. Okay. um, then a residual connection added to the input to the attention output, followed by layer normalization. What residual connection means, whatever we have processed and what in the beginning input we had given, both are getting added and passed to the normalized there, and then it is passed to the next feed forward layer. What is feed forward layer? It is basically a two-layer neural network applied independently to each positions. How it works, we will see. Then again, the same process happened. The serial connection and normalization are applied once more time, as we have seen into architecture also. Then whatever the output is there, that is passed to linear layer. Uh, uh, it basically it convert into this all your token into logits. There, this is a kind of final product we get after this processing through transformer block or all the layers. And finally, what we do, this softmax function is applied on the logits, convert the logit into probability over the vocabulary. So this convert those values to probability, and final output is probability distribution over all the possible next token. The token with the highest probability is selected as the next one. This is what happened. I'm sure if you're listening first time, you have not understood anything here till here. And whatever I've talked about this process. So not an issue. We will just try to explain these things into more detail, then you will be able to understand it. So if you see that decoder only architecture, more carefully. So if you will see there are three uh, section kind of, or high level section kind of thing. The first level, what you see, that's it is pre-processing kind of things. You give some input, it gets converted to embedding, then positional encoding is added into it, and then it is passed to the transformer block. A transformer block, what happened here? One mask multi-head attention um, uh, is applied on this, and what it does, it add attention to the words that we will see. So we have converted till now. What we have done, we have converted word into number, added position to it, and then in this mass multi-head attention phase, we add attention to it. What attention? What is this attention? I'm talking so many times. It tell the words how it is related to other words, and because the next work prediction is depends on all these things. Okay, so after that, there is a two simple things happen for both the layer, mass multi-head and feed-forward layer. What happen? We add the input to output and normalize it, and the same thing. Then it is passed to feed-forward layer. Again, output of feed-forward layer is um, a residual connection is added, and then normalize it. So these four things happen in transformer block, and finally, after processing, we apply linear layer, um, and there we get logits. Logits is what basically in all the dimensions we get the highest value. I mean, its value. Every word has, after all this processing, every um, we get a number for every value, and when we apply softmax function to that value, it gives probability, which basically the highest probability value gets generated. So that as a output probability. So this is what happened high level. One thing, if you see carefully with the previous architecture in decoder part, there multi-head attention is also involved. But in decoder only architecture, we don't need multi-head attention. Why? Because we are also not using encoder only, encoder architecture, right? So what I'm trying to say, let me just clarify here only. Where is that? Yes. If you see here, whatever encoder left side things, process input, then pass it to multi-head attention. This is called cross attention also. So when we have encoded, that time we need multi-head attention, and then it will have also um, add and normalization. Right? But if we are not using encoder architecture, then we don't need this layer. So it will have transformer block will have only two layer: mass multi-head attention and feed forward attention. It will not have multi-head attention layer when we are using only as a decoder only architecture. If we are using both encoder and decoder, that time it will be there. This is very important to understand. It is not clear for many people. Mm. So we have talked about this thing. We will now, what we will do, we will go one by one, all the layer in detail. And finally, when we go through all the layer detail, then we will be able to understand. So pre-processing layer, but with one of the important thing is embedding, which we have discussed many times also. What is embedding? Embedding refers to a technique used to convert high dimensional sparse data into lower dimensional dense vector that capture the semantic meaning or feature of the data. It reduces dimensionality and captures semantic relationship. What is meaning of this? We need to understand two things. What is high dimensional sparse data and lower dimensional dense vector? Let us see first this. High dimensional sparse data. High dimensional means the data has many features or attribute. For example, if you represent each word in a vocabulary of 50,000 words, each word in a vocabulary of 50,000 words as a one hot vector, each word is a vector of 50,000 dimension. Sparse means the most of the value are zero in a one hot vector, only one position is one, indicating the word, and the rest are zeros. So, so you see, if we have a, for example, suppose if we have a vocabulary of 5 words, right? Apple, banana, cat, dog, and elephant. So if you want to depict any word, so how we will depict it? We will write 0, 0, 1, 0, 0. This is called one hot vector because you see it is only representing position of the cat. We might be able to find. It does not provide more information about it. There's no any other feature information is available. Only related to positions, right? So there is a five answer, only one non-zero value. That's right. So it does not provide much information about cat. And what is lower dimensional dense vector? Lower dimensional means fewer feature, that is 100, 300, 550,000. Dense means most are all values are non-zero and they carry meaningful information. Like the word cat might be represented as 0.12 minus 0.45, 0.333, say in 300 dimensions. This is a dense embedding. It captures semantic relationship like cat is closer to the dog than to banana. What it's meaning? It is basically when we convert a word into a embedding or when suppose dense embedding. So B include many features, property or information about a particular words. Here, like suppose if you try to represent someone, maybe Mukesh. So we don't know which Mukesh you are talking about, right? But suppose if you give it 300 features, right? He is from Bangalore, he's an IT, he is this and that. So anybody can identify that Mukesh, right? The same thing is here. When you represent a word into embedding, you gives a lot of information about it, of course, in numerical value. And that is basically we have got some semantic meaning of it or information about it. It helps to identify that particular words. Hope it is clear now. Let me just go ahead. I will telling, we have already discussed this. Sparse vectors are inefficient, don't capture meaning. Dense embeddings are compact, efficient, and capture semantic similarity. Hmm. Some more information, like again, we have suppose vocabulary size 5, embedding dimension is 3, then the embedding matrix, how we represent something like this. Each row corresponds to a word, for example, cat index 0, embedding point 1, point 0, point 3. So if we have a model which has only 5 words like this, and it embedding dimension is 3, means it will have 3 features for all the words. And then it will be represented in a matrix like this. And how we can find out any words actually embedding value? We will convert into a hot vector, and then if you multiply this matrix to, then it will give you the exactly its embedding value. Actually, when I say this embedding value, how let me keep all this at the time of training. Training it gets created, and that is what we use for prediction. Like for GPT-3 vocabulary size 50,257 and embedding dimension is 12,288. So suppose we want to convert cat to a vector in GPT-3, it will be represented something like this. It will have how many value? 12,288 features of it, so values of it. And if you have some, and it has so many vocabulary, right? 50,257. So how this matrix multiplication will work? You have one hot vector, which will have 50,257 values, right? One position is for cat, so it will have one there, and it will multiply. So we will get this cat value, this cat actually embedding value. So this is what happened internally. Hmm. Oh, embedding we have understood. What we have understood in embedding, a value is converted into embedding and with respect to LLM based on what is the embedding dimension is. And what is dimension? It is a number of features we put about a token. Here we have taken token words to be the same. So this is what we hopefully now it is clear. Here's some more examples how we convert. So if you see here in cat is converted into um, embedding vector size of 512. So it will have so many values, and it has position also into that vocabulary. So here you see the position, and here you see the embedding. So this is what kind of things happen when we talk converting into embedding. Okay, so now we will see next things in pre-processing, positional encoding. A transformer process input token in parallels, not sequentially. This means they do not understand the order of words in a sentence. Whether the is came first or cat has come first, it is not able because it is processing parallelly. To fix this, we add positional encoding to the input embeddings to give the model a sense of position or order. Okay. How it is calculated? It is a little complex. Um, simply, it is basically we use sine and cosine functions, and this formula is used where we have position and this model. So this you can use this formula internally used to calculate the positions. I think it's okay if we don't go in detail. Just you need to know okay, this maybe we can calculate that position of the uh, every position of the what you say embedding value, right? So if you represent cat into 512 dimension, it will have 512 values, right? Every value will have position. So that's it is added. Here it is. Here cat is second word of a sentence. Or POS is one, positions is one, and it is represented at encoding vector dimension size 12, and I value include 0, 1, 2. Each position gets a vector. Mhm. So there is two things are important. One is position of the word in dimension, in vocabulary, and what is its dimension. These two things are important. That is used into this formula position. If you see sign position, then I what represent every value of the embedding of that word. In diagram, it can be represented, and why that's a position, how it help to know the position. Here, if you see x-axis encoding dimension feature that describe position, y-axis actual encoding value, which can be positive or negative. Lines each word's unique encoding pattern based on its position in the sentence. So, see, based on this patterns, model is able to find out the position of or value. Model is able to find out the position of the token. Here, if you see the negative values also there, why? And the sine and cosine function naturally produce values between -1 and 1. These ups and downs create waves like patterns that help the transformer model recognize the relative position of tokens and understand order. These patterns are added to word embedding, giving the model both the meaning of the word and its position in the sentence. So these values, whatever we calculate, that is added into embedding, and this provide using these values, model can find out the position of the token. You see this, the you see the diagram is like this, or the picture. If you see the function like cosine and sine naturally represent a pattern that the model can recognize as continuous. So relative position are easier to see for the model. Here you can even you can see the pattern what is described. So finally, we will have a complete example of word embedding and positional embedding for vocabulary cat, dog, apple, banana, car, and embedding dimension 3. So the model adds the word embedding position coding vector element wise. Like say, what finally what we get word embedding plus positional encoding. Word embedding, and finally we get the. It is basically what happened. We add both the matrix value, and it provide information related to position also. So what we have understood two things: embedding and positional encoding. Embedding, especially how it is get converted into a vector, dense vector, and positional encoding, how we use trigonometric functions to get the value. Perfect. Now we will move to a transformer block. Transformer block, before we understand what is mask multi-head attention, we need to know about uh, self-attention. Okay. In self-attention, the term self highlight the model is paying attention to different part of the same input sequence. Self-attention allows the model to examine how each element in a sequence relate to the other within the same sequence. There is one thing in that previous definition of self-attention, input sequence. What is input sequence? During text generation, the input sequence consists of the original input prompt plus all previously generated token. This combined sequence is what the model uses at each step to generate the next token. What I'm trying to say, if you chat with ChatGPT, so if you first you have entered what is weather like, it will give you some answer. Again, you have asked something, it will give you answer. This complete conversation is input sequence, right? So that's we need to. It is not the whenever you enter that value, that is a input sequence. This is important to understand. And the meaning it gives, attention the new prompt will have, new token will have is with respect to all the previous tokens you have entered. So this is the little complex part. And I say when you try to understand this decoder only architecture, the most difficult thing to understand is self-attention. If you are able to understand self-attention, how attention get calculated, then I think every other things will fall into place. So first, how it is gets calculated, two things happen into self-attention. First, each word embedding converted into query, key, and value. And second things what happen, we calculate self-attention using this softmax function. Softmax function into V. V is value. Yeah, so this is totally new concept. So we will understand slowly. So first thing, what convert each word embedding into Q, K, and V. What is QKV? The query query Q, key K, and value matrices are core components of the self-attention mechanism in transformer model like Word, GPT, and others. For example, in the sequence, the cat sat on the mat because it was tired. To understand what it refers to, the model need to attend to cat. That is where Q, K, and V come into picture. Is what how a word is related to any other words in the same input sequence that we find out using attention mechanism. Right? There Q, K, and V, query, key, and value comes into picture. As told, as we discussed, query, it asks what this token is looking for, then key give you idea what this token contains, and actual value is the V. Okay, what I'm trying to say, something like this. If you search on that some movie sites, what is the movie related to love? So there are different keys, right? A kind of dictionary. So you have romantic, action, science fiction, and so these are key, which is category it says, and then value, actual value, you have that value name of the movie. So it will something like this. If you search love, it will do some more semantic search. It will be more matched with the romantic, right? And then it will give you the movie name might be title. Right. So this is the way it works. Some more example. If you write dogs on the beach to search something like this, so it will match with wherever it match more, that it will get um, it will search and give it a result to you. So these are example of this. So we will just try to see how we will calculate Q, K, and V for any embedding value. So to compute Q, K, and V, we apply three separate linear transformation to the token embedding. What do you mean by three separate linear transformation. Actually, suppose we have some embedding value of cat. So what happens? It is multiplied with three uh, bit matrix, and then it gives some value. What I'm trying to say is that you see it happens something like this. If you have embedding value of cat, suppose, so we will have three bit matrices, like what for q k b, it will multiply and then it will give a value, right? This um, and I'm only talking about one word till now, something like this. Suppose if you have cat, embedding values point 0.5, 0 0.5, 0 0.4, 0 0.6, 0.9. So how we will get this embedding q, k, and v? It will be multiplied to three different bit matrices, which is randomly generated, and then you get the three value for this cat, something like this. Multiply this, you get one value, then second. So now we have calculated q, k, v for cat only. The same thing, the same process we have used for other the and sat also. So we have got all three values for it. So this is the way you calculate query key and value for any embedding value of a token or any bird. Then we have to use this formula to get the attention value. Uh, uh, mm, we will not directly calculate using this thing. We will do it step by step, right? Like first we will calculate attention score. Attention score is what? Just multiply q of cat, all the k values of all the value, all the whatever the input sequence we have, all the tokens k values there, right? So what we are trying to find out, we are trying to find out how cat is related to every other words in the sequence. And how you get it? You multiply query of cat to the key of every other birds of the sequence, right? So like we are asking it how you are related to the, how you are related to cat, how you are related to sat. In fact, it asks related with itself also. So when whatever the multiple value we get, it gives attention related to different words in the same sequence. Different words, right? Okay, so this way it will comparison happen. Here, if you see in all the three multiplication, we have q value of cat only. Cat is multiplying with key of the cat is value is multiplying with key of cat, and cat query value is multiplying to uh, key of sat. So whatever, if you see the value 1.25, 0.5, 1.5, so this is giving attention value of cat with respect to the with respect to sat and with respect to itself, right? And based on this probability value, next word is decide. So it is provide attention score or something more we have to do with this to get the final value. So we have got attention score of cat. There is one more operation happen. What happened? That's we scale it. I mean, whatever the key vector dimension is, that you take the root of that and then divide it. What why it is useful? It gives a bigger. It gives a smaller value of this. It gives. It gives and it helps in using this attention value to score something, right? So first we have calculated attention score, then we have scaled it. Scaled it means we have divided by key vector dimension root square, and then we have got scaled attention score for cat, right? After that, you need to apply softmax function. If you apply the softmax function on the skill attention score, you get a value. And what happened when you applied a softmax function to any or this vector? It gives you probability, right? And if here you see, but if you add all three value, it will be one, right? So So here and maximum value, what you see, that's maximum value is for SAT, right? So this means this what it represent? It represent after cat, um, cat has more attention to SAT, so there is a chance after cat SAT will be predicted. Okay, the same way we have we can get the attention weight for the and attention weight for SAT. Here, if you see attention weight for SAT, then what happened? Its attention weight with respect to the is very less, 0.32. Its attention weight is compared with respect to cat is lowest, and its attention weight for itself with itself is highest, right? Because no other word we are calculating after this, right? Only these three are there input sequence, and it has just been predicted after cat, so there's no chance of getting cat after it. So that's why this the score it represents this. There's very important concept you will be able to understand if you see clearly the attention weight of the. It has 0.26 attention weight with itself. It has 0.37 attention weight with cat and 0.37 attention weight with sat also. So why cat is coming after this? Why not sat? So that's you need to understand it. So this is what we need to understand, right? So we have calculated attention weight for applying softmax functions. So we have now attention weight for cat, the and sat, and we'll go for the next step. Only thing is that we need to understand this is the uh, probability distribution value calculated according to the whatever the formula we have used. But there are other things also involved into predicting the next word, right? Semantic meaning, how the model is trained. So that also come into the picture when we predict the next one. Okay, we'll go ahead and see how now multiply the attention with value vector to get the attention output. So how we do that? We use this formula. Although we have already seen that softmax qk transpose divided by root dk into v. How it actually happen? You add all the attention value and multiply to this value. All you add all the attention bits and multiply to the value. Something like this. If you have attention bit for the 0.26, 0.37, 0.37 value vector, the value vectors what is there for the this one for v the cat this one for value for sat 0.91 0.1, right? We compute how you multiply these values with the vectors and you get a value. So this is the way we calculate attention output, right? And the same way we calculate the for the we can also calculate for cat and sat. So finally, how we got it here? First, we calculated k, uh, q, and v, query keys and value from embedding vector of a word. Then we calculated attention score. We scaled it. Then we applied softmax functions and multiplied with values of all the words, right? And then finally we got the output sequence. It has all the attention meaning with it, these values. How we this is the way we went ahead, right? Embedding vectors converted into QKV, then attention score is scored using that formula. Then we scaled it, attention weight we calculated, and finally we multiply attention weight with value of all the birds and then all the tokens, and then we calculated attention output vector. So this is the way we calculate self attention of any embedding or word embedding, right? But that is not actually used in GPT. There's something more. There's something called multi-head attention. Multi-head attention is just multiple self-attention mechanisms running in parallel. instead of having just one way to focus multi-head attention, let's the model look at the sentence in multiple ways at the same time. Each head will learn to focus on different relationship. One head might focus on who is doing the action, another might focus on where the action happens, another might look at the grammar structure. Then all these heads are combined to give a richer understanding of the sentence. What I was trying to say, see, we have calculated self-attention using one head, one uh, you can say processing unit. Internally, it has many, any LLM model has many heads. Okay, and these values are these heads process the input sequence differently to get the different meaning of it. So that's we calculate this way. So this is called multi-head attention. Once every head provide output, it is getting added, and then um, finally we get the attention value. But that is multi-head attention. There is something more of when we talk about mass multi-head attention, and this is also a little tricky to understand. Right? What is self-attention? Each words look at all other words to understand context. Multi-head attention is what? Multiple self-attention layers run in parallel to capture different types of relationship. That's also be understood. Now here, what is this mass multi-head attention? This is a mechanism used in the decoder part of the transformer architecture to ensure that during training or generation, each bird can only attend to itself and the birds before it, not the one that comes after. It works by applying a mask over the attention scores to block access to future position, preventing the model from cheating by looking ahead. This masking is applied across all attention head. What it trying to say, let us see with some example. There's something called casual masking. So you go through this process only, the same process. You get the QKB, then you get the attention score, then you get the skill attention score. And before getting the attention bit, you do some casual masking. What is the casual masking? That's we will see. One very important thing, which we sometimes it is not clear to many of the people. When we talk about encoder, it has self attention, but it does not have mask multi head attention or casual. It can see the whole input sequence. Mask means what? You don't see a model does not see the future um, token, future embedding, word embedding, right? Then there's a decoder one. This uses mask self attention, but cross attention does not uses mask multi-headed. It can attend to the full encoder output. So only decoder only models use mask self attention. Okay. Mm. How to apply casual masking? And this is what we will try to understand. Then everything will be clear. Casual masking ensures that its token can only attend to itself and previous tokens. Means the prediction for position I only depend on the position of I only depends on positions less than equal to I, not future token. It is implemented by adding a large negative number like minus infinity to the attention logic before applying softmax, effectively zeroing our attention to those positions. Let us see what it's trying to say. We have got skill attention score, right? So it has we have got skill attention score for the we have got skill attention score for cat. We have got skill attention score for sat, right? How we will apply casual masking here? You casual masking so that its token can only attend to itself and previous token. So we mask future token by setting their score to minus infinity. So you see the attention score with respect to with respect to others future token, which is cat, and this thing is multiplied by negative here. So now it does not have any score related to the future token. Model will generate the next word in the same. If you see the mask For cat, the attention score is only previous token, the or itself 0.35, not with SAT, because it doesn't know about the SAT till now. The same way, mask score SAT will is with itself, with all of it. So you see, it now it knows the attention score of the cat also, right? Why this is? Because the future token or embedding model will generate not from input sequence, it will generate from the vocabulary it has, right? It will predict the next word. So that otherwise, what happens? It will take it from input sequence only, right? So when you give some input, model will start generating next word using its own logic, and that's why mass multi-head attention is used. It only has attention stored with itself or previous token, not with a future token. So we do something like this: we multiply some negative value, negative value, or big value to this future attention token, and then we apply software function. And when you have very negative value, minus infinity kind of things, it will become zero when you apply software function. And so now you see this is the correct attention bit in mask multi-head attention. In multi-head attention, you don't need to perform this step because though in multi-head attention or encoder only model that has bidirectional, they know about all the birds. But in decoder only architecture, which generate new word, there you are not aware of the model is not about aware of the future words. Hmm. So so to get attention vector, we must multiply attention bit to values that we have already done previously also. So here BC something like this, 0.37, and now here you can see one very important point also. We were discussing once when the has both the value 0.37 for cat, 0.37 for sat, then how it will generate, how it will, which one will get generated, right? So here we have calculated attention score after applying softmax. So finally we will get this output vector after mask multi-head attention, uh, mask multi-head attention steps. So how mask multi-head attention happen? First we have queries, keys, scores, and then we get attention scores. We apply attention mask, then we apply softmax function, and we get only attention score related to the current words or previous words. Okay, this is what mass multi-head attention is. After that, we have two steps after this processing. These are the mm, normal steps for feed forward layer also. This first we a residual connection is added, means the input to the sublayer is added to its output. Okay, then the result is passed through layer normalization to stabilize the learning. Okay, what is residual connection? Like if you have input vector this, output vector this, then it gets multiplied. That is residual connection. Layer normalization is what? The technique is to normalize the input across the feature of single data point given input vector x with element x1, x2, x3, and perform the following. This formula is applied for all the whatever the value we have. The latest calculate layer normalized for the token, the residual output itna, then compute means you have to compute like this, then 0.300 plus 1.70 divided by 2, and then we have to compute variance, then you have to normalize, and final normalized value you get. So we need to use this formula to get these values. The same thing we can apply for cat and the sat also, and we get the values. After that, the output is passed to the feed forward network. The FFN is in each transfer block is identical and independent of its position. It is position wise. It usually has this structure: max 0 x w1 plus b1 to w2 plus b2, something like this. What is meaning of this? Basically, if you see in detail, there is a three things happen here. The first, a linear transform is, if you see x w1 plus b1, that is one linear transformation, right? You have input value, then you multiply by it and biases and add biases into it. Then you apply, but you see max, zero, and this x w1 plus b1 bracket. That is basically, we are applying a ReLU activation function. We can also apply GILU. And finally, again, we do the linear transformation, something like this. ReLU function, we know how it works. If you apply ReLU function on some value, if it is less than zero, the value will be zero. If it is more than zero, the value will be the same. That is the ReLU function. Although it looks very simple, but it's very important for neural network, other complex calculation. So we will calculate this feed-forward network, something like this. If suppose if you have X matrix, then you have the two bit matrices, two biases. If it's the first linear layer, what we do, we expand it. So if you see now, if we have X as matrix 1, 2 into 1, so we will multiply by 4 into 2, right? So we will get a, and we will add, finally we will add bias to it. Basically what we have expanded this value to capture more meaning, more information related to that embedding. Then we apply ReLU functions, and finally we again bring it to the previous mm, size or value, previous dimension. So this is what actually happened in feed-forward network. The most important thing is what? It expanded to capture more meaning, and then you apply a ReLU activation function and bring it back to the previous system. With, of course, having more information related to it. The same thing I have explained here also for the way it happened. We need to keep in mind the feed-forward layer transfer each token vector individually. It expands the vector to a higher dimension, apply non-linear activation, and then compress it back. This helps the model learn richer representation beyond what attention alone can capture. If an output is passed to add a norm layer before finally sending output to the linear layer, this is what the same thing happened, which we have just seen mass multi-head attention. After that, residual connection is added, input and output value, and then it is normalized, right? Finally, so we have completed pre-processing, we have completed transformer block, how mass multi-head attention work, especially this casual attention, how gets calculated, that important. And then finally we pass whatever the transform block has got it to linear layer. Here. A linear layer, what happened? Whatever we get the output, that we multiply with the bit matrix and then add bias to it. One important thing is we need to understand the bit matrix what we had. That's it's dimension and vocabulary size. That's we need to care about. And this bias is also the vocabulary size. So it happens something like this. If suppose we want to compute logits for a vocabulary of 5 words, right? So in vocabulary we have 5 words. Suppose the cat sat on the mat, and we have FN output 0.05 itna, right? So then we need to take a matrix of dimension size as this vocabulary size, right? And we have if an outputs 2D, so we will of course will take two dimensional. So this is what we will use to calculate the value in logits. We will multiply that things and we'll get this kind of logits here. If you see here, a cat has the highest value. So this is the actual output after doing pre-processing, transformer block processing, and then we get the logits. This is the final value we get to all the what it has. It's, if you see the highest value, whichever the word has or token has the highest value, that will get predicted next. So after the here it is cat is there, so that will be predicted next. But before that, we have to use softmax function using this formula, and that's if we apply that formula, or that subnet function, it will keep the distributed uh, probability value. What do you mean by distributed probability value? If you calculate, add all the probability value of these words, these tokens, it will come to one, right? And here the highest value is cat. So next word will be cat will be predicted. So all the probability come doing this work. So finally, how what we did, we have entered input, then decoder, we added all those things which is required. We converted into embedding and positional encoding, then provided it to decoder. Decoder did all its works. It did mass multi attention, then um, FFN, feed forward network layer worked on it. It gives the output to linear layer, which produced logits. And finally, up on the logits, we applied softmax and we got the highest value. So this is what happened in decoder architecture. Basically, what here two things you need to keep in mind. We have taken only example of five vocabulary size and two three dimension for embedding. Actually, in LLM, like for GPT-3, there, as we have seen, there is 50,000 plus vocabulary size and 12,000 plus dimensions. All the operation happen in that way. Word is converted into 12,000 plus dimension, and vocabulary is 50,000. So we use calculation happen in that case. And when you try to understand these things, you just keep in mind how it will happen there when so huge number of vocabulary and dimension is there. Maybe in GPT-4 and all, there's a more dimension and vocabulary. So hopefully you are able to understand how the next word probability value got calculated after going all through these phases. Thank you. Thank